Okay, so I shall record my lesson. Okay, so do you still remember what we did the last lesson? So basically, we talked about the importance of recognizing whether upon mixing, there's a reaction or not taking place, right? Okay, so if there's a reaction taking place, what do we need to do? If there's a reaction taking place, you need to write the equation. Then what else do you need to do? ICF table to calculate which one is limiting. Then you find out what is the resultant reaction mixture. So resultant reaction mixture can become a buffer or just a salt solution or a strong acid in excess or a weak acid in excess. Okay, so all this combination will result in different calculation approach, hence affect how you calculate your pH. Correct? Right? So this is what we have done last time. Okay, so we have gone through the answering of question 1, except for 2, and all the calculation part. Okay, so we have also gone through the concept of the acidic buffer and basic buffer, whereby if I have a weak acid with a Ka value larger than the Kb conjugate base value, then I know that I'm forming an acidic buffer. Remember this concept? Okay, so if I have the acid which is a very low Ka value, then the Kb of the conjugate base may be larger, then it will result in a basic buffer system, even though it's a weak conjugate acid base pair of a weak acid. Okay, but when we calculate the pH, we are still treating it as a weak acid dissociation, Ka. Can? All right. So this is where we stopped last time. Okay, so for part C, right, there's this question. Why is it that HCl and sodium chloride, which is a conjugate acid-base pair of a strong acid, not a buffer system? So what will you say? Anyone? What will you say? Why do you think a strong acid, conjugate acid-base pair of a strong acid cannot buffer or cannot resist pH changes when small amount of OH minus or H plus is added? What do you think? Okay, Sebastian, what will you say? Okay, wait. So in this case, right, complete reaction meaning being a strong acid undergoes complete dissociation. Yeah. Okay. So what you're trying to say is a strong acid undergoes complete dissociation. So the consequence is okay. Conjugate base is going to be a weak base, and is even a weaker base than water. All right. Then we will not react with water to give OH minus. What's the relevance of that? Yeah, so typically when we write equations to explain buffer system, right, we know that the conjugate base is the one that will remove the H plus. Okay, while the molecular acid, or rather molecular acid will remove the OH minus. Correct? So we know that this is no longer present because it undergoes full dissociation. Yeah. Okay. So even though this undergoes full dissociation, it will still be able to neutralize any amount of OH minus that is added. Okay. So if you add OH minus to this solution, it can sort of buffer the change. Yeah, because the OH minus added, whatever amount added can be removed by the H plus, the large abundance of H plus coming from your strong acid. But on the other hand, if you try to add H plus, can your chloride remove it? Yeah, no. Okay, so this is something that you need to emphasize. Chloride being a weak, very weak conjugate base is not able to remove any small amount of H plus. Okay, so therefore, there's no way it can resist pH changes due to the addition of H plus. Okay, so we have to come from a perspective of how buffer works. Yeah. Hmm? The weak acid, the undissociated weak acid, will be the one that removes the OH minus. Through dissociation. But then there's a lot of H plus. So when the OH minus is added, right, there's no reason why the dissociated H plus doesn't react with it. For weak acid, because we have large abundance of the weak acid as well as the salt. Large abundance. So large abundance, when it's present in high concentration, it has a higher likelihood to meet the OH minus. But in this case, all the acid is already fully dissociated. So there's no more HCl molecule, but only H plus. So H plus is the only one that can interact with the OH minus. When I have a weak conjugate acid-base pair of a weak acid, right? Remember, we always emphasize large reservoir of the weak acid, large reservoir of the conjugate base. Yeah, so having large reservoir, actually the free H plus in the system is actually very little. Yeah, so the likelihood that the OH minus meets your weak acid is much higher than the dissociated H plus for that system. Yeah, Ken? Yeah. Okay, do you understand what Faria just asked? She asked that, why is it that for a buffer system, when we have large reservoir of the conjugate base pair of a weak acid, we always use the weak acid. We always use the weak acid to remove the OH minus, right? Okay, why don't we use the H plus to remove the OH minus, even though essentially it's the same thing? Both are acid-base reaction. Okay, so remember, when we have a large reservoir of the weak acid, for example, CH3CO2H, yeah, large reservoir, then we also have this present in large reservoir. So remember, this being present will suppress the dissociation of this weak acid as well. So you can see that in this buffer system, the amount of free H plus you have is actually very little compared to the large reservoir of the weak acid, large reservoir of the conjugate base. Okay, so that's why when you add OH minus, the OH minus has a greater likelihood to meet this than to meet this. Do you understand what I'm trying to say? This present in high concentration, this present in low concentration. So when you throw in a little bit of OH minus, right? What is the chance of meeting the weak acid? What is the chance of meeting the free H plus? It's more likely for the OH minus that is added, right, to meet the weak acid than the dissociated H plus. Get me? Right?
Because the dissociation of the H plus is suppressed.
Yeah, the dissociation of the weak acid is suppressed. H plus is already dissociated.
So because it's suppressed, then the concentration is high.
Yeah. No, we spam the weak acid, we also spam the salt one. Yeah. So the weak acid dissociation is suppressed as a result because of the high concentration of the salt. Yeah. So in this system, it will be the weak acid that removes the OH minus. Okay, but for a strong acid, there's no more of the molecular acid. So we are only working with this. Okay? Okay, so with this in mind, right, should I go through the titration curve first or should I go to question 2 first? Up to me. Okay, so let's look at question 2. Okay, question 2 is more like explanation type. Okay, so for those who are still fuzzy about where to identify the main buffer system or buffer region, Okay, we'll go through that later on. Okay, let's quickly look at question 2A. So for this question 2A, right, there are several parts to the question that you need to explain. So upon dilution, pH increases and eventually reaches a static value and does not change upon further dilution. Okay, so these are the things that you need to explain. So why is it that dilution, the pH will increase? Chen Hao, what do you think? Why dilution will cause the pH to increase?
Because the H plus dissociates.
How does that help in explaining pH increase?
Because pH is a measure of extended dissociation.
Is it? Remember, pH is negative logarithm of H plus concentration. It's an inverse relationship. So with this in mind, right, what does it mean? So when you dilute it, what does it mean? H plus concentration increases, decreases, or increase.
Because the H plus dissociation.
So
then it's
increase.
Yeah.
Dilution. So when
H2 like H2
originally is already 1 mole per dm cube. So in this 1 mole per dm cube, before you add water, right? Is it a full dissociation? Yeah. So already at 1 mole per dm cube is already full dissociation.
So decreases.
Okay, so decreases. Why so? Yeah. Okay, so upon dilution, the H plus concentration will start to drop because the total volume increases. So as the H plus concentration drop, then the pH value will start to increase. Right? Okay, that's logical, right? Yeah. So can someone tell me what is this static value that we are talking about? What is this static value? Huh? Yongwei? Auto-ionization of water. So what is this static value? Okay, so we are assuming 25 degrees Celsius. So at 25 degrees Celsius, it will reach the static value of pH will go towards 7. Okay, and does not change upon further dilution. Okay, why so? Why so? What will you say? What will you emphasize in your discussion? What will you emphasize in your discussion? It's already fully dissociated. Yeah, remember, we are working with a strong acid here. So it's already fully dissociated. So there's no so-called suppression. Okay, so it's not about suppression, but about what? Yeah, it's negligible. All right, yeah, so as with infinite dilution, the H plus contributed by our HCl becomes negligible compared to the H plus from auto-ionization of the water. That's why it will approach 7 and reach a static value. Okay, all right, so this is what you need to emphasize over here. Okay, so dilution causes the concentration to drop, therefore pH increases. So with infinite dilution, okay, so as it approaches 10 minus 7, this implies infinite dilution. Okay, so with infinite dilution, contribution by your water becomes significant. So the concentration total, right? Concentration total will be contributed by 2 sources. One coming from your strong acid, one coming from auto-ionization of water. Okay, then of course, the H plus contributed by HCl will become negligible. Okay, as what we have discussed, with infinite dilution, H plus from HCl will become negligible. Hmm. Because you add in a lot of water. So as you add water, total volume will continue to increase and increase. So the concentration of H plus from HCl will continue to drop. Yeah, because if you spam a lot of water, right, essentially the whole system becomes more like water than HCl. Yeah. Why can't it become basic? Why will it become basic? Water also, but then you still have the H plus that is still present, contributed by your HCl. So even though it can become negligible, but your H plus is still slightly more than the OH minus. It can only become alkaline if your OH minus can be more than H plus in your water. So is it possible or not? Can your OH minus surpass the concentration of H plus with infinite dilution? Not possible. So it cannot become alkaline.
But there's still like a little bit of
Yeah. No. You must remember that we can only describe a solution to become alkaline, provided that the OH minus larger than H plus. Yeah. So will it come to this situation? Ask yourself. Is it possible? Not possible, right? So how can it become alkaline when you recognize that OH minus cannot exceed H plus? Okay, so is it okay with this part? Any other question that you need to clarify with me? All right, so let's look at part B. Part B is working with the, actually you have seen this in one of the checkpoint, right? Okay, I'm not sure whether you still remember. So if you calculate the pH, right, if you manage to calculate the pH of the strong acid 6.82, huh? Yeah, I know that the question did not request you to calculate, but then if you did not calculate, how will you know that the statement is true? Okay, let's say you calculate arbitrary. Okay, so in this case, right, how do you think I get this value? Let's say if the question asks you to calculate, how do you think I get this value? Because if you look at the value, the concentration of the sulfuric acid that is given to you, right, is a 10 minus 8. So when you do a negative log of 10 minus 8, the pH will become more than 7. Right? So does it make sense? So how do you think I got this value here? Auto ionization of water. Okay, what about that? Yeah. Yeah. Okay, so because of the very, very low concentration of your strong acid, you have to consider the contribution by your water from the H plus. So in this case, right, in order to get this value, you have to remember that sulfuric acid per mole gives you 2 moles of the H plus. Okay, so this will be times 2. Okay, so the concentration of H plus of this from your sulfuric acid will be times 2 of this. Then you have to add the concentration of H plus contributed by your water. Then you can calculate the pH to be like this. Yeah. So like what Yong Wei has said, right, it's important to recognize that when your strong acid is extremely low in concentration, contribution by water becomes significant. This is what we had discussed earlier also. When it becomes significant, you have to consider the total contribution. And that will enable us to obtain this pH value. So do you know how to calculate this value? This one should be able to do so, right? I won't show you the working. You go and calculate. Okay, so what do we need to emphasize here? So what is the chemistry principle? What is the chemistry principle? The pH value is never a measure of acid strength, right? Yeah, so this is the chemistry principle here. pH value itself alone is not a measure of acid strength. Yeah, so in fact, pH is dependent on two things, right? So I need you to recognize this. H plus depends on the initial concentration of the acid as well as the degree of dissociation. So even though sulfuric acid is a strong acid, but its initial concentration is much lower. Actually, I've let you copy this in your notes already somewhere. Yeah, if you recall. So this is the chemistry principle. So we cannot depend on pH value to tell about acid strength. Okay, it's never a measure. Okay, so instead, right, you should compare H plus versus the concentration of the acid to tell the acid strength. Okay? The H plus and the acid is different. Acid, I'm referring to the whole compound before dissociation. Okay, so this is what I'm talking about, acid. HCl, ethanoic acid, phenol, benzoic acid. Okay, these are my acid. So H plus is after it dissociates. Okay, so do not get confused. When I say H plus, is the free H plus. When I refer to acid, I'm referring to the molecular acid. They are different. Okay. All right, so let's look at the next part. All right, so what is important in this question? Can someone tell me? So what do you think the question is trying to ask you to explain? What do you think the question is asking you to explain? What do you think? Pardon? Acid-base reaction is a complete reaction. Is there an acid-base reaction here?
Just strong acid versus weak acid.
Yeah, it's a metal acid reaction. Okay, not acid base, but there is a reaction. All right, so there's a reaction taking place. And if you look at the paragraph here, right, what is important? What do you need to pay attention to? What's important? Okay, so there's a difference in strength. HCl is a strong acid, while your ethanoic acid is a weak acid. So there's a difference in acid strength. Okay, so that's number one. Number two, what else do you need to pay attention to? Yeah, same volume. So they give you the same U of product. Why same U? Both react to completion. Okay, what enable both acid to react to completion? Yes. Okay, so the excess zinc must be mentioned in your answer. Okay, so because without the excess zinc, it will not cause your acid to react to completion, especially the weak acid. Okay, so that's why. Okay, so other than recognizing that we are comparing acid of different strengths, strong acid, weak acid, okay, we recognize that there is a reaction, and this reaction is a complete reaction. Okay, so strong acid, of course, undergoes full dissociation. Then for weak acid, it will be a partial dissociation. Okay, so for partial dissociation on its own without any reaction, right, the weak acid gives you much smaller amount of H plus. Okay, so even though it gives you a much smaller concentration of H plus compared to your strong acid, but there's no worry of it giving you less of the hydrogen gas. Why so? Why so? Yeah, according to Le Chatelier principle, as your H plus is being removed, as it reacts with the zinc, right? The H plus will be removed. Okay, so as the H plus is being removed, then the equilibrium, the position of this equilibrium will move forward. Okay, will move forward. And it doesn't stop when it reaches a new POE. It will continue to be moving forward because you are spamming zinc. Yeah, you keep spamming your zinc, right? So the H plus will be continuously removed until all the weak acid is 100% dissociated. Yeah. Yep. Pardon again? CMF meaning? Oh, yeah, that means I need to redo everything. Thank you for telling me. Okay, so full dissociation, partial dissociation. So despite the changes or drastic difference in the H plus concentration, it will still give rise to the same U. Okay, so the mentioning of the strong acid versus the weak acid, right, is to explain that there is a lower concentration coming from your weak acid. So despite having lower concentration of H plus, there will still be a full dissociation. Okay, so essentially, right, this is the most important part. All right, with excess zinc, acid, doesn't matter whether it's strong acid or weak acid, it becomes the limiting agent. So therefore, it becomes the one that determines the U. Yeah. Okay, so recognize that from the volume and the concentration given, right, you are having the same mole of the weak acid and the strong acid. Because of the given volume and concentration, you have same mole of the strong acid and weak acid. So therefore, it gives the same volume of hydrogen gas. Okay, why same volume? Because we recognize that excess zinc enable your weak acid to undergo full dissociation. And it will give the same mole of H plus as strong acid. Yeah, so despite of acid strength, they will go to full dissociation when there's a reaction. So in this case, the reaction involves a metal-acid reaction. Yeah. So in other words, if there's an acid-base reaction, it will also go full dissociation. Yeah. Yeah. Because potentially, right, the weak acid gives you the same amount of H plus. Oh, the reason why I emphasize access to you is for you to recognize that my weak acid will undergo full dissociation. Yeah, it's to make sure that weak acid fully dissociate. But the same amount, meaning I will have to calculate the mass, telling you the mass, and then you can deduce that is 1:1 ratio or 2:1 ratio, 2 of the H plus to 1 of the zinc. Yeah. So by telling you excess, right, you are very sure that all your acid is reacted away. Provided zinc is added in stoichiometric amount. Yeah. Yes. In this case, is Le Chatelier principle. this is the essence of what's happening. So if you want to bring in the Le Chatelier principle, so you can say that it will undergo full dissociation because of the continuous removal of H plus that keeps pushing POE of equilibrium 1 forward. Yeah, so this is your Le Chatelier principle. And how much you need to write depends on the number of marks given. Okay, so you have to look at the marks given, then you determine how much you need to write or elaborate. Okay, any question? If there's no question, then I'll continue. All right, so we are done with this part. Okay, then I'll continue with the titration curve. Okay, so question 6a is very straightforward. We just calculate, right? So can someone tell me what is the significance of this H plus concentration? What's the significance of this H plus concentration? What's the significance of this H plus concentration? It comes from the spontaneous dissociation of the acid. There's no disturbance introduced. Okay, so this is the free H plus concentration coming from the spontaneous dissociation of your acid without any external disturbance. Okay, Ken? Huh? Yeah, so you have to express it in this form. You're not supposed to leave it as 10 minus 3.5. This answer is not acceptable. Is this what you have? No, he's asking, can you leave his answer like that? Is it? Cannot. You must express it in this way. This is called standard form, is it? Okay, Ken? All right, so let's look at part B. What is part B doing? Part B is you are creating a disturbance. And what causes the disturbance? Yeah, the reaction, the acid-base reaction. So this acid-base reaction causes the disturbance, removing the H plus from the weak acid. So eventually, right, at this volume, all your acid will have be fully dissociated. Okay, so using the titration result, this titration result will give you the concentration of the acid. Okay, and it will also be equal to the concentration of the H plus because at this point, it has undergone full dissociation. Okay, all right, so this is what's happening. So with this in mind, amount of H plus will be equals to the amount of HA is equals to amount of H plus, which will be equal to the amount of OH minus. All right, so why do you think the values are different? Okay, so how do you talk about it? In apple juice, it undergoes natural partial dissociation, but with the presence of your acid-base reaction. So this is the equation representing the acid-base reaction. So because of this acid-base reaction, which is a complete reaction, okay, the H plus that is present in the system is completely reacted away with every drop of OH minus added. Okay, so as a result, right, it will enable your weak acid to undergo full dissociation. Okay, so for part A, this is to account for part A. It's a spontaneous dissociation of your weak acid. Then this is to discuss the disturbance. This is the cause of disturbance. So because of this disturbance, H plus is being reacted away. Because it's an equilibrium. So as your H plus is being removed, more of HA will dissociate. So as it is being reacted away bit by bit, your HA is also there to dissociate, to supplement it, according to the Chapelier principle. Yeah. Can? Right, so if you're comfortable with this, then we'll look at the titration curve. Any question to ask about this part? Anyone of you who wants to volunteer to explain your thinking process for titration curve? Huh? Anyone? Then I just hand the whole tablet to you. Huh? Okay, so if you look at the axis, of course, you have your pH versus the volume of sodium hydroxide. Okay, then per CMQ. So this is the first thing you'll do. Write down the axis first. Okay, then we have the initial pH, which is already given in the question. So on its own, the weak acid undergoes partial dissociation. Initial pH is 3.5. So here is my 3.5. Then I estimate where my 7 is. Okay, so 3.5 is there, right? 7 will be twice the length, aggregation, about that. No need to use the ruler to measure, but cannot be drastically different. All right, so if this is where my 3.5 is, then 7 will be double the axis. Can? All right, so this is where my 7 is. All right, so in this case, right, if I do a very quick rough sketch, I will expect this to be the trend, because I started off with acid in the conical flask, then my sodium hydroxide will be added in excess, right? So it will move towards the pH of the strong base. Okay, so what's the next thing I should do? Can someone tell me? If you don't want to bring, can you tell me what I should do now? Okay, label the volume. Which volume? Equal? Okay, the neutralization volume. So neutralization volume is also given in the question, which is 27.5 here, right? So this 27.5, I can indicate over here. So this is where my 27.5 is. Yeah, so where is my max buffer? So if I look at this titration curve, you have weak acid in the conical flask. So as you add sodium hydroxide to it, it will be progressively, slowly converted to the salt. Okay, so before you reach the equivalence point, this is what you are going to see. From volume 0 towards the equivalence point, you will have weak acid swimming together with its salt. So what kind of reaction mixture is this? It's a buffer region, all right? So buffer region, what we are interested in is the maximum buffer point. So where is this maximum buffer point? Yeah, half of the equivalence volume. So this will be half of it. So that will be 27.5 half. That will be 13.75. Okay, so at 13.75, I'm going to have a max buffer. So this max buffer point, right? Does it have a special pH value? This max buffer point, does it have a special pH value? Syed, what do you think? No, no special. So I cannot calculate the pH. We can calculate. So what's the calculation of how to calculate? Yeah, so how to calculate pH of a buffer system? Can you help me recall the equation? pH equals to Ka, where you have pH already, so this one should be pKa. Okay, then plus logarithm of what? Yeah, the salt or the conjugate base over the weak acid. So in this case, when it's half neutralized, what does it mean? So at the point 13.7, it means that the weak acid is half neutralized, right? Yeah. So these two will exist in equal ratio at the max buffer point. So it's essentially logarithm 1. So logarithm 1, the whole thing will become 0. So at that point, pH is equals to pKa. Correct? So do we have the Ka value? Yeah, we don't have the Ka value, therefore we have to calculate the Ka value here for this question. Yep. Maximum buffer, label the pH. Yeah, so as I plot it, I will place the corresponding value here on the axis. Yeah, so is that how you want me to, that is how you label it, the pH value? Is it needed? Yes, it's needed because you need to plot where your pH value is so that it can join up the points. Okay, so how do you calculate the Ka value? How do you calculate the Ka value? Ka value is equals to Kw over Kb. Do you need that? Yeah. So Ka value, how do you calculate that? Yeah, H plus square. Why is H plus square? Yeah, the equation. So for weak acid, upon dissociation, H plus and the conjugate base will be 1:1 ratio. Okay, so since they are 1:1 ratio, it will be just like a H plus square. Do I need to do it this stepwise? Okay, so it's a A minus, right? Then divided by the HA. Okay, so for Ka expression, we will calculate using the concentration at equilibrium. Okay, so for Ka calculation, we'll use concentration at equilibrium. So concentration of H plus and A minus at equilibrium, they are equal to each other. Okay, since they are equal, then I can simplify my expression to be H plus square divided by HA equilibrium. Okay, so the H plus will be 10 minus 3.5 whole thing square. Yeah, then how do I calculate the HA at equilibrium? How do I calculate that? Am I able to calculate that? Yeah, the concentration calculated by you, right? The weak acid is a here. So this is the weak acid concentration. Okay, but this one is the initial, not at equilibrium. So how do you calculate the concentration at equilibrium? Yeah, so you can minus. So in this case, concentration of HA at equilibrium, it will be 0.11 minus 10 minus 3.5. Yeah. So with this, you can calculate the Ka value. So if you punch into a calculator, right, what's the Ka value? (9.12 times 10 minus 7). So did all of you manage to get this? So once I have the Ka value now, then I can calculate my corresponding pH, right, for my max buffer. So what will be the corresponding pH for max buffer? 6.04. Okay, so now I need to shift my point nearer to 7, 6.04. Okay, so this is my max buffer point. So I have 1 point here, volume 0, 1 point here at 13.75, max buffer point. Okay, then next, this is where my equivalence point, right? 27.5 is 100% salt solution. So if it's a salt solution, I need to ask whether the salt can undergo hydrolysis. So can the salt here undergo hydrolysis? Yeah, it can, right? So when this salt undergo hydrolysis, basic salt or alkaline acidic salt is the basic salt because it's a weak acid, strong base titration. So it's a basic salt. So this means that I will have a midpoint pH higher than 7. Okay, so this one is more than 7. More than 7. Then I should put a vertical line equal above and below this point. Okay, so remember the pH of this salt is the midpoint of the steep change. Okay, so I'll put equal length here. Then after I'm done here, what is the next point that I need to plot? Yeah, so what is the end point? It will approach the pH of your sodium hydroxide. So what is the pH of your sodium hydroxide? Is a 0.1 mole per dmq, right? Your sodium hydroxide. Yep. Okay, so it will approach 13. So you just need to draw a horizontal line that corresponds to your 13. Correct? Okay, so when you join up the point, it will be from here to here to here, and it will approach 13. Okay, so this is equivalence point. This is your max buffer. Okay, so this is how your titration curve will look like. Any questions so far? Wait. Hmm? Hmm. This portion. So how will you draw it? This way. Okay, can you explain why you draw it this way? But this is your buffer region. So by right, as it approaches the max buffer, the change in pH should slow down. That's why I draw it this way. Logical or not? So this is where your max buffer is, right? So the change around here should be minimal. But when you draw it this way, it suggests that the change is more drastic when it's nearing the max buffer. So it doesn't make sense. Ken? Any other question? Yeah. Straight line, what straight line? This straight line? Smooth. Yeah, straight line. I mean, even though in reality, it may not be exactly very straight. It can be a very steep slope. Yeah, but for your sketch, right, we allow you to just draw one straight line. Yes. Because this is a weak acid, strong base titration. So my salt is basic. Remember this one? The parents? Yeah. Okay, any other question about this part? Yep. Okay, if they never ask, they never specify, then you just indicate whether it's more than 7, 7, or less than 7. Yeah. So if the question did not specify any calculation, this will be enough. Okay, any other question? So if you're asked to calculate pH of the equivalence point, then you need to consider dilution. Because the total volume now becomes 27.5 plus 25 is a liquid. Yeah, 25. Yeah, you need to consider dilution. Any other question before I move on? Yep. Endpoint. No. Endpoint is the equivalence point if you choose the right indicator. Yeah. So indicator is the one that gives you the equivalence point. Indicator is the one that gives you the endpoint because of the color change. Yeah. So endpoint is always experimentally determined. I see a color change, that's my endpoint. Yeah, but if I choose the correct indicator, then my endpoint will be very close to equivalence point.
So we use this to determine whether we dilute.
Pardon again?
We use this to determine whether we
Dilute what?
dilution.
Dilution of what? You mean dilution of the salt?
13.5 to 27. 13.75 to 27.
Yeah. Uh-huh.
So that's dilution.
There is, because the total volume has changed. Then relevance?
So diluting the NaOH.
No. NaOH is your title, the one from the VRET.
Also,
Before equivalence point, all your alkali is removed, limiting.
so what are we diluting?
Oh, so I'm saying that if you are to calculate pH of the salt solution, then you have to recognize that the total volume is 25 plus 27.5 at that point of time. If you're calculating pH of the salt. Yeah.
Then if it's the buffer, the max buffer, then it's
Max buffer, no need to calculate because your ratio will be 1:1 anyways. So pH will be equals to pKa. No need to consider dilution.
oh, so dilution is just for
Salt
to determine pH.
of the salt. Okay, can? All right. Okay, so suggest a suitable indicator for titration. Explain your choice. So what will be a suitable indicator here? Because the pH change is in the alkaline region, so I should choose an indicator working range in the alkaline region as well. Okay, so it's either phenolphthalein or thymolphthalein. Okay, so the working range, as mentioned, you just need to explain that it coincides with the steep change in pH at equivalence point. Okay, so do you know what is the expected color change? What will be the color change? Purple. That is the final color. Then before that, color change means initial and final color. Also, what is the initial color? When you are asked to describe a color change, there must be initial and final color. Yeah, colorless to pink. Pale pink. Yeah. Okay, because it's only one drop. All right, Ken? So if you use thymolphthalein, right, it will be colorless to pale blue. So remember, you have to describe a change. Okay, so can I quickly go through this part? calculate the concentration. You have done it, right? So I just quickly go through the answer. So the concentration here will be the neutralization involving your H plus. But please take note, your concentration of sulfuric acid here, the concentration of your sulfuric acid here is that of the H2SO4. So the concentration of H plus is actually 0.05 mole per dm cube. Okay, so when you calculate the amount of H plus, you have to multiply by 2 first. So only 10 cm cube is used for titration. So you need to convert to per dm cube. Okay, so you need to check the mole ratio as well before you do any calculation. So far, so good. Right, so determine the Kb value. So determining the Kb value, we'll use the ice table because we need to work with concentration at equilibrium. Okay, so working with concentration at equilibrium, initially, this is what I have. None of the salt is formed. Okay, then the change, it will dissociate to form this. So at equilibrium, this is what is left. So you just substitute it back into the Kb expression. You should be able to calculate it to be this way. Can? Okay, so just remember that when you calculate Ka or Kb expression, you need to work with concentration at equilibrium. ICF table. Oh, there's no, it's not a reaction. It's just weak-base dissociation. ICE table. We are asked to calculate Kb of amine. So on its own, it undergoes partial dissociation. There's no reaction here. Yeah. So whenever you're asked to calculate Ka or Kb, there's no reaction. Hmm? So pH is equals to 11.8. So POH will be equals to 14 minus 11.8. So that will enable you to calculate the OH minus concentration. So remember, when you're working with the base, you have to work with the OH minus. Can? Right? So do I need to bring you through the titration curve again? Or should I just show you the answer? Okay, are you able to sketch? Or just leave blanks for me to tell you the answer? Couldn't do B. So now can you try the sketch? If you're not sketch. No, it's a negative log of 0.1. So negative log of 0.1 is 1. So that is POH. Therefore, pH is 14 minus 1. Yeah. But it's a strong base, so the calculation is quite fast. If it's a weak base, then you need to do the Kb expression. Yes? Pardon again?
Why we can't use this equation for any table?
You can, but this one you have to work with the equilibrium. Because, okay. So you don't rearrange lah. You just like, So is it drastically different?
It's 5.40, 4.90.
Okay. Sorry, did anyone use this instead? So you use the concentration of OH minus equals to square root of Kb multiplied by concentration of your amine. Yeah. Okay. So in this case, right, because whenever you use this expression, you are always using the initial concentration. Then this one is the already dissociated. Yeah. But in this calculation that we are doing here, right, we are using equilibrium concentration instead. So the value that you have calculated here is somewhat close. Yeah. So for our team, right, we have decided to, okay, so if you look at the A-level examiner's report, they actually don't mind you using the initial. That means you can skip calculating the equilibrium concentration. Yeah, so if you use this approach and you calculate a value, it's 5 point something, right? 4.98. Oh, 4.98. 4.98 times 10 minus 4, right? Yeah. Okay, so that we will also accept. Yeah. So by right, if you look at your notes, when you're asked to calculate Ka and Kb, we always ask you to work with concentration at equilibrium. I don't know whether you remember or not. Yeah. That is because we know how much has dissociated. Therefore, we can calculate the equilibrium. No, it's from the from what you have given, what is given here. This is the spontaneous dissociation of your weak base. Square root 1, yeah. The square root 1 is coming from here also. You see, if this is x, this will also be x. So what you are calculating is the unknown x. That's why the square root comes about. That's how the square root comes about. The answer is different because in this case, we always take it to be initial. But in my calculation approach, I calculate what is at equilibrium. So that makes the slight difference. Yes? Pardon again? This one? Yeah, can. If you, because when I teach you, whenever you use this expression, right, it's always the initial. Yeah. So if you can remember, you replace it with at equilibrium, then you should be able to get the same answer, right? You know? Because they are essentially the same thing. It's just how you rearrange. Yeah. Can? Yeah? Am I confusing you? So it's a matter of whether you are working with initial concentration or concentration at equilibrium. That's all. Can? All right. Any other question? So I show you the curve. So I show you the answer. Then you ask me question about it. I hope you have done the sketch. Okay, so this is what the curve will look like. Okay, so remember, whenever you have the weak acid or weak base in the conical flask, your max buffer will occur before the equivalence point. Okay, so whenever you have a weak acid or weak base in the conical flask, your max buffer will occur before the equivalence point. Marking point. All these are marking points. Huh? The one that I label over here, these are all marking points. So you need to label the max buffer point, need to label the equivalence point, and need to indicate whether it's acidic or alkaline. Yeah. Origin, meaning? 0. Does it matter? If you write it there, then doesn't matter. It has to be from 0, but if not, then this cannot be the initial pH. The 1.3, right? This has to be at 0 volume. Oh, okay, sure. Okay, any other question? You have to try it on your own. Don't just copy. Copying doesn't help because A level, there's nothing for you to copy from. You have to sketch the titration curve yourself. Yeah, so you must know how to sketch, how to get the points. Okay, so in this case, right, can I go back to your notes? I need to go back to the poly basic titration. Okay, so can I refer you to this part? Okay, it's on page 49. Poly basic titration curve. Go wash your face. So polybasic, what does it mean? Okay, especially for weak acid. So you can see that there is a significant difference in the Ka1, Ka2, and Ka3 values. Okay, so this is your sulfurous acid, is a weak acid. Sulfuric acid is the one which is a strong acid. So when you work with sulfuric acid, being a strong acid, it will undergo full dissociation to give you 2H plus. Whereas for a weak acid, it will be a stepwise dissociation. Okay, as you can see for yourself that the difference in Ka value is a -6, power 10 minus 6. So it's a significant difference, hence it's a stepwise dissociation. So having a stepwise dissociation will also tell you how many equivalence points you should have. If you have 2 Ka values, then it will be 2 equivalence points. If you have a tribasic acid, 3 Ka values, right? Then you end up with 3 equivalence points. Okay, so this is the thing that you should see. Right, so quickly, right, let's look at work example 12. And as you look at work example 12, I would like you to consider this question. In your pair, you can discuss.
So then buffers like 2. But then how the second one? That's part of it. This is what it
That's
is.
all.
Let's go.
Yep.
This right. The pKa, right? So it's Ka of the weak acid, right?
Mhm. Are you done? Yongwei, you're supposed to discuss. Can discuss with Sai.
Oh my god, how did I do that? I think strength is the one that's here.
Done? Okay, so let's look at this part. Right. So please take note, what accounts for the initial pH here? Can someone tell me? How do I calculate the initial pH here? The sulfurous acid. So sulfurous acid, I'm given two values, Ka1 and Ka2. So for initial pH, what should I consider? Okay, only Ka1. So for this initial pH, only Ka1 is contributing the H+. Okay, do you still remember why so? Yeah, Ka2 being the weaker acid will be suppressed by the Ka1 stronger acid. Okay, so contribution by Ka2 will be negligible for this initial pH.
Ka2 is suppressed by Ka1.
Yep. Okay, so can someone tell me why is it that the volume required to reach first equivalence point 25 and another 25 for the second equivalence point, even though there is difference in acid strength? Yeah, so Ka1 and Ka2, even though they differ in acid strength, they potentially give the same amount of H+. Okay, so despite difference in acid strength, they potentially gives the same amount of H+ upon full dissociation. So therefore, they will require the same volume of sodium hydroxide for complete neutralization. Ken, am I making sense? Okay, so the next question I ask you is points of maximum buffer. So where is the points of maximum buffer? Okay, remember in your conical flask, you have your weak acid. This is where your weak acid is. This is your strong base. Yeah, so it will be half of the equivalence point. So this will be 12.5, 12.5, the first max buffer. So the first max buffer here, who is the buffer system? At this first max buffer, can someone tell me what makes up the buffer system? Yeah, the sulfurous acid and its conjugate base. So remember, the conjugate acid-base pair only differ by one H plus. So this is the conjugate acid-base pair who will buffer against pH changes. Okay, so this is the first max buffer. Okay, so the second max buffer will occur at here, right? 37.5. So this is where the second max buffer is. So in this second max buffer, what makes up the buffer system? Yeah, the hydrogen sulfide and your SO32 minus. Right? So remember, this is the acid. This becomes the conjugate base. In the first max buffer, this is the acid. This is the conjugate base. Okay? So if I ask you to come up with equations to illustrate how it resists pH changes, you need to know which one is used to remove the small amount of H plus, small amount of OH minus, which one to be used. Okay? Then the next question asks you for account for the pH for the first and second equivalence point. Now, if you look at this, right, A, it doesn't quite fit because normally when I have a weak acid, strong base titration, my salt will be a basic salt, right? A, but then the first equivalence point has a pH obviously less than 7. But why? Why so? Yeah, so in this case, you must recognize that at the first equivalence point, your Ka1 is completely gone. At first equivalence point, your Ka1 acid is gone. All right? Then Ka2 starts to come in. Ka2 starts to come in, yeah. K2, no, the H plus. When I compare H plus, not the Ka value. H plus of the acid plus H plus of the water. Not the Ka value. Okay, so in this case, what happens? Second acid dissociation takes place. So at the first equivalence point, Ka2 starts to take place. Ka2. And if you really want to calculate the pH at that point of time, you need to consider dilution. Okay, you need to consider dilution. So if you were to calculate pH at the first equivalence point, you need to consider contribution by Ka2 only, and you need to consider dilution. Okay, all right. Now, any question? Any question? Now, yeah. So in this case, right, your KB1, all right, KB1 will be this. So how do you calculate the KB1 value of sulfide? What is this value? It will be 10 minus 14 divided by 6.6 times 10 minus 8. Yeah, KB1. Because as a base, right, it will take the first H plus. Okay, I don't label KB. KB of sulfide. KB of sulfide, it will be 10 minus 14 divided by 6.6 times 10 minus 8, right? Then what is the value here? 10 minus 6. About that? One point five times 10 minus 7. So what's the significance? Yeah. Understand where you're coming from. But according to this graph, right, is accounting for the the acidic part is coming from the Ka2. Okay, but Sebastian is quick to see that Kb of your sulfide, but then, no. At this point of time, there's only hydrogen sulfide. Okay, sorry. So we should be talking about this. Because at that point of time, sorry. So at that point of time, at the first equivalence point, you only have this. Yeah, so how do you calculate the Kb value of this? How do I calculate the Kb value of this? What should I use? It should be the Ka1. Sorry. All right. So there's nothing wrong. So it should be this one that we are considering of. So we have to calculate from the Ka1. So Ka1 is 10 minus 2. So the Kb value is actually very, very small. Yeah. Okay. So therefore, it's more of an acid than a base. Okay, so this one is correct. Oh, do you understand what's going on? Sorry. It's just a one-to-one conversation. No, it's not the criteria for buffer because Sebastian recognized that hydrogen sulfide can be an acid, a proton donor, or can be a base to accept a proton. Yeah, the HSO3. The HSO3 can lose a H plus to form sulfides, or can gain a H plus to form sulfurous acid at that first equivalence point. Okay, so in this case, if I were to consider it as a base, I will need to calculate the Kb value, right? So the Kb value will be to be obtained from here. And it points to a very, very weak base. The Kb value is a very weak Kb value. Yeah. So we'll see it as the acid than the base. Yes? Is it can still dissociate what? 10 minus 8. Partial dissociation. What about the concentration? Higher. Concentration of this sulfurous acid? 0.2. Don't understand. Again? Because Ka2 can take place now. I think you are confused. When we compare with 10 minus 7, right, is the concentration of the H plus of the acid versus the H plus from your water, not the Ka value with the H plus of the water. Yeah. This is the base. Yeah. Okay, so when it's a base, right, the Kb value will be obtained from here. When this is the base, the corresponding, yeah. So when I have a 10 minus 14 divided by this, then the corresponding Kb value will be 10 minus 12, right, around there. So it's very small. So it's a very weak base, a stronger acid. Yeah. Okay. Am I confusing you? Again, sorry. Any question? Because the second volume required is another 25, right? Yeah. So half of the second volume is 12.5. Then add on to the original 25. Because this one is in the order of increasing titration result. Yeah. So you have another 25 CMQ equivalent. Half of it is 12.5. Okay. Any other question? Yeah. The species present is hydrogen sulfide lah. Yeah. No, as a base, it can undergo proton transfer with water ma. Yeah. So I'm saying that it's more willing to donate H plus to water than to accept a proton from water. Yeah. So it's the hydrolysis equation. Any other question? So what is this? This is an alkaline. It's an alkaline pH because you end up with this as the salt, and this can only be a base. Okay, so sulfide here can only be a base. It's a basic salt. Okay, so if you write the equation to represent this, it will be sulfides reacting with water to form your hydrogen sulfides and the OH minus. So this will be the equation. This will be the equation accounting for the alkaline pH here. Okay? Make sense? Okay, any other question? Right, very quickly, right? Because the next question in your tutorial refers the understanding of the aspartic acid. So for aspartic acid, please take note, we are working with the fully protonated aspartic acid. Yeah, fully protonated meaning we consider carboxylic acid, and the amine side group, right, is also an ammonium cation, fully protonated. Yeah, it's triprotonated.
How about the H also?
CH, you mean this one? This one is not acidic, it's a CH bond.
So that one cannot be H plus.
Cannot. Okay, so in general, please take note, for fully protonated aspartic acid, you have to remember this trend. Acid strength will be, all right, this is the alpha carbon. Have you learned this in bio, alpha carbon? Yeah, so alpha carbon is the carbon whereby it is directly bonded to amino group as well as the carboxylic acid group. So this is the alpha carbon. Okay, so alpha carboxylic acid will be a stronger acid than a side chain acid. So this is the side chain acid. It's a carboxylic acid at the side chain. This is not bonded to the alpha carbon, so it's a weaker acid. Okay, then if you have an alpha amino group, then this will be a stronger acid than a side chain ammonium salt. Okay, so this will be the general trend. Yeah, so if I ask you to sketch a titration curve, you must recognize that the first equivalence point will correspond to Ka1. So this is the first equivalence point. Then the second equivalence point will correspond to Ka2. Then the third equivalence point will correspond to the Ka3. Okay, so at the max buffer region, this will be in equilibrium with the ammonium salt. This one. at the first equivalence point, max buffer region, this is the large reservoir of the salt, large reservoir of the corresponding acid. Okay, so at the second equivalence point, what is the species? Okay, it will be this and this. Okay, so at second equivalence point, this is already lost. So there's second H plus being dissociated or neutralized. Yes? Top and bottom meaning? Don't understand. Uh-huh. Oh, okay, understand. So at the second equivalence point, this is the second dissociation taking place. Okay, yeah, right. So at the second equivalence point, this will be my acid. This will be my salt at the second equivalence point. Okay, then at the third equivalence point, it will be here to here. Then you have the last dissociation. Can? So it's progressive loss of H plus. So Ka1 first, followed by Ka2, followed by Ka3. Okay, so understanding this will help you in the next tutorial question. So can you complete the rest of the tutorial question? The next time I see you, I'll go through them. Okay, right? So if there's no further question, we'll end our lesson here. Additional question, I will ask you to do it when relevant. Remember, Friday seminar lesson, please bring your nitrogen compound lecture notes. Yeah, we're going to resume nitrogen compound.